Hey guys, my name is Jani and this is Optofility Test Corner. This is a series of episodes where we have been talking about Waveguide displays, how they are designed and manufactured, and what kind of problems you can see on the production line. Today we talk about how to detect the problems early on in the production, and discussing about this subject with me is Joonas Pylväinen from Optofility Finland team. Joonas, welcome to the show.
Thanks, Jani. Thanks for inviting me. It's always a pleasure to be here.
Well, it's good to have you here. So we have two examples that we wanted to go through. So maybe we'll start from those.
Yeah. So thinking about the whole production line, of course. First of all, when the waveguide is being manufactured from the wafer level, there might be issues first of all in the front end. So front end is basically where, for example, if we are talking about diffractive waveguides, the actual structure is imprinted on the resin or on the glass. And then on the back end, that is then the point where some modifications, like for example edge blackening or stacking or actually cutting the waveguide out of the wafer is happening. And maybe as a first example, one could be for that at the waveguide level, if you do image quality measurements, which is usually quite late point to find the issues, you might see some problems with sharpness, so with MTF, or maybe the uniformity of the whole field of view that you are seeing is not what you are expecting, and you start going back to process phases, and maybe it wasn't anything in the back end, and you later find out that the issue has been in the front end, for example. And there, at least, especially when talking about nano imprinting, where we are using this kind of intermediate soft stamp to actually imprint the structures onto the resin that is being used. So that is a flexible material that is under a lot of physical stress when the stamping is happening. So there is of course degradation happening there, and the stamp, for example, can be stretchy.
So basically, in the beginning of the production, when you have the stamp, traditionally, if there has been a problem there, you would see it in the end of the production line in the image quality. But that is super late. Like if you think about all the processes you have already done, and then you need to throw the final product away. So what you are saying is that we have a way to actually detect the problems already on that phase.
Yes, that's exactly. So doing it in the image quality measurements is way too late. You may have been producing days or several batches at least poor quality. So you need to be able to detect it before that. And for that one, let's say in the case of this uniformity issues, where basically the path of the light inside the waveguide has been changing, that could be caused by a change in the period of the gratings, for example, in the diffractive waveguides that has the gratings. So instead of them being exactly like you have designed them, they are physically in the stamp, they are stretching bit by bit the more you are using the stamp to imprint your waveguide.
And then how do we detect something like this?
So for that one, we have a tool called the WGAT, so GAT, coming from the name of Grating Analysis Tester, so testing the diffractive gratings. And with that tool, you can observe or test and measure the period of the gratings very accurately, and also the orientation of the gratings. So
you would be able to place your wafer into our tester, and then the tester automatically tests desired measurement spots from the wafer.
That is correct. So you can use it for wafers, you could use it for the hardmaster, or you could actually use it for the diced waveguides as well. Let's say for development purposes, but maybe not on the manufacturing line anymore.
Mm-hmm. Got it. And then how precisely can we measure something like this?
So with the GAT, we are kind of looking into the grading area as precisely, of course, as possible. We are looking at picometer accuracies over the area that is being measured, and that is something that is needed for the waveguide gratings to be kind of functional as they have been designed.
And why would somebody choose to use this method versus something else that is on the market?
So the GAT is using the litro measurement method. So basically it's a diffractometer. So it is using a laser being diffracted from the gratings, and we are doing the measurement based on that. So we are measuring the +1, -1 diffraction orders with it. And the key thing there is that, sure, you get the period and you get the orientation. Those are very, very important to kind of follow up in development and also in the manufacturing. But of course, SCM or something, you can get the actual grating shape out of the waveguide. But the problem is with them is that if you do it on a manufacturing line or a large scale, it means that you need to destroy the waveguide in order to get the result. So with the GAT, it's a non-destructive way to get the grating period and the grating orientation measurements from the sample.
And I also understood that it can actually measure much bigger area at a time compared to, for example, the electron microscope.
That's correct. So the beam size there is a bit more adjustment, but while we for the microscopy, let's say the electron beam microscope, we are looking at kind of a singular grating. With the GAT, we are measuring an area of a millimeter, or let's say in millimeters spot size. So we get a larger area and the period information from that.
And then if you think about the image quality, I guess it's even better image quality metrics to actually average like a bigger area of the waveguide than just go and look at one really small area.
That's correct. So if you, for example, want to find out what is the grating uniformity or the period uniformity, let's say, over the whole kind of optical element area, with the GAT, you can scan the area. Instead of, for example, if you would go to SCM, you would need to slice the sample multiple times, which probably would break the sample in the end, and then get the same kind of a scanning information about the period and the orientation.
Got it. So then you also said that its stretching might cause problems with the image sharpness. So how can we detect something like that?
So the problem there, first of all, is coming, of course, when you are changing the period, you are changing the angle of the light, how it travels in the waveguide. So in diffractive waveguides, for example, there are multiple paths that the light is taking. So if the paths are not equal, you will get images that are not overlapping. So you are kind of losing the sharpness of the image. And one way, for example, to detect this, of course, would be with an image quality tester at the kind of image quality measuring phase, so in the back end. But again, best would be that it's figured out, or the problems are figured out already before that. But with the good image quality tester, you can get all of these metrics, and you can also go back to the GAT tool and see if the problem is root causing from the gratings or if it's something else entirely.
So do we have then some kind of image quality tester that we could use for this?
Yes, of course we do. So for that one, we would have the WG IQ, which is an R&D tester. So it's meant to support different kind of tilt and wrap angles for the development work where you need to, for example, more precisely scan around the sample and see all the angles and maybe measure multiple eye box positions across the waveguide.
And that is actually a tester that is right behind me here.
But of course, the kind of R&D development type of precise tester that is not very scalable for production, where you need more or less the throughput, which is the most important part. So for that one, we have a new product family. So basically production IQ, that is called. So a version of the tool that is meant for the manufacturing environment.
And then how does that differ then from the R&D version?
So the key difference there is that the whole kind of a unit has been simplified, so it fits better to the manufacturing environment. It has less kind of gadgets to adjust with, because in the manufacturing environment you use the R&D tester to find out what is critical to your quality. Let's say it is the uniformity, for example. And then you only measure that uniformity in the manufacturing. Yeah.
And then now that you also brought that uniformity into the picture, is that something that WG IQ can also then measure?
Yes, among many other things. So
yeah,
WG IQ can measure, well, already mentioned the MTF, but then uniformity, of course, contrast, kind of ghost measurements as well, and then color uniformity and the color itself. So it is very kind of all-around test system to have to get all metrics measured from a waveguide.
And then normally when people think about image quality measurement, they think about a display that already has like the light engine on it, and then that shows the image on the screen. But in this tester, we don't really need to have the fully functional display yet. Is that correct?
That's correct. So the test system itself has our own designed projector on it. So it is not a digital projector, it's an analog projector. So it also removes the problem of projecting pixels into a sample and then measuring those pixels. So we get input an analog image into the waveguide, and then we measure it with our own camera system as well.
Got it. And that also means that we are able to do image quality measurements again quite early in the process. So we don't need to wait for the final, let's say, module assembly.
That's correct. So we can do the measurements one step before that, so it can be ensured that only the good waveguides, they are passing forward downstream into the assembly before you are wasting a projector or another type of cover glass, for example, glued on it.
Yeah, and sooner you catch the problems, the cheaper it of course is. If it ends up into the final product, that would be the worst case scenario. So of course we never want that to happen. Yeah. Then you said that we had the other example was from the dicing part of the production. So let's talk about that.
So for example, now that we have passed the front end, we are coming into the back end processes. One good example from the wafer dicing, so where you actually cut the waveguide out of the wafer, either by a laser or by some sort of mechanical process as well. So that one can create a kind of a rough edge for the waveguide, and maybe in the worst case it could chip away parts of the edge as well. So the chipping itself, that should be visible by visual inspection. If you look at the waveguide, you can see that okay, the edge is kind of chipped, but then the roughness on the edge, it might not be visible to the eye. But then when the sample goes forward, let's say for the image quality measurements, what happens with the rough edge is that the light is bouncing back into the waveguide, and depending now on the edge roughness, it bounces back differently. So if you have a very rough edge, the light is scattering more, and if you have a clean cut edge, there should be more of a singular beam, or let's say not a scattered beam, it's not a singular beam. So that, for example, with the image quality tester, you can see this reflection, if not directly, depends on the physical shape of the waveguide, of course, but it's usually visible or very visible in the contrast measurement, for example. That the more scattered light
you mean
have
that
from the edge.
Then basically black wouldn't be as black as it should.
Exactly. And in the worst case, if it would be really worse, you would have only a gray image, of course, because your blacks and whites are kind of on the same level in the image.
Yeah. And this is again something that we can use WGIQ to then measure.
Yeah, exactly.
Yeah. So let's put on the screen now the familiar picture that we already looked at in the previous episode. So that shows the production process of the waveguides. And we have now basically showing there which part of the production we can use different types of testers. So should we quickly just walk through that?
Yeah, so first of all, in the upper part of the S-curve, we basically have the front end where the wafers are being imprinted. So in that phase where we are talking only about the gratings and the waveguide is not yet functional to show the image, the testing would be mostly with the GAT for the grating period and the grating orientation. So that's the first part, and for example in manufacturing that could be used kind of as a sampling method to test every 10th wafer, every 25th wafer, every 50th wafer, to get the kind of statistical chart where your process is going. Then basically on the second row we are looking at the back-end processes, and now depending on how the line has been arranged, there might be more or less boxes there. But here, depending on how the line has been arranged, you could do the waveguide measurements maybe already from the imprinted wafer itself, so kind of wafer level image quality measurements to catch them early, or maybe you have diced them, maybe you have already stacked them and you use it kind of as an outgoing quality check before the stacked and ready waveguide goes into the assembly.
Got it. And then looks like we have two testers here that we haven't talked about yet. That's Scout and then Body. How do those kind of relate to this waveguide production?
So for the production itself, they are maybe not like a production tools, but more like a performance tools that can be used then in the end when you have the ready product. So for example with Scout, you could do image quality measurements on a headset level when you have assembled the headset, and then afterwards when you have all the software and all other things in the headset and it should be ready to be worn by a customer, you could use the body to do kind of sensor testing and to kind of see how the sensors, software and the image are working together basically in the tool.
So
sorry,
like
not in the tool but in the headset.
Yeah, so basically like a system level testing.
Exactly, system level testing, and exactly for this kind of temporal phenomena, that how is the image tracking compared to your head movement? Is it jittering around? Is it staying stable? Or what is the kind of a combination of all those devices and components that you put into the headset.
Got it. So yeah, I think we now pretty much covered everything we wanted to talk about today. So for the audience, I hope that you guys were able to see what kind of testers we have, how those testers can be used in your production, and how you can detect the problems early on in the production rather than later or even in the final product. So Joonas, it was really good to have you. Thank you for explaining all these testers and the challenges on the production line to us.
Thank you very much. It was great to visit here again.
Yeah, thank you. And thank you guys for watching. And we'll see you in the next one.
Thank you. Bye-bye.
Bye.